welcome to Melbourne Museum and the 2022 Museum Lecture Series. I'd like to begin by acknowledging the traditional owners of the lands where we work and where we meet tonight, the Wurundjeri and the Boonwurrung peoples of Eastern Kulin Nation and First People language groups and communities across Victoria and across Australia. And I pay my deep respects to elders past, present and emerging, and also acknowledge we're guests on their country. So my name is Dermot Henry. I'm Head of Sciences here at Museums Victoria, and I'm delighted to be hosting this evening's lecture, and would also like to acknowledge my colleagues Dr. Kate Phillips and Dr. Moya McFadgen from the Natural Sciences and the Society and Technology departments who are convening this lecture series. And I recommend that you go to our website and look at future lectures that are coming up. The Museum Lecture Series seeks to connect the public with the important and wide-ranging research work of the museum staff and our collaborating researchers from not only across Victoria and Australia, but also overseas. The lectures also showcase our collections, which in turn inspire and facilitate inquiry into some of the region's key contemporary and historical questions, and they highlight our collaborative partnerships. Tonight's lecture, fresh approaches to deep time, a significant fossil can be cool, I think you will enjoy. This is a chance to get to know Koolasuchus, Victoria's recently appointed fossil emblem, and learn how it connects us with life in deep time. So why do we need a fossil emblem? State emblems recognise and celebrate the natural history of their region. Victoria has designated floral and faunal emblems, so you might be familiar with, for example, Leadbetter's possum and the weedy sea dragon, and also gold is our mineral emblem. But unlike other states, it did not have a fossil emblem. In fact, the Queensland are just now running a campaign to nominate a fossil emblem as well. Fossils capture the imagination, and we know that this can be a gateway to young people pursuing a career in STEM. The geological history of Victoria stretches back over 600 million years. Geological maps are beautiful, they're very colourful, but they convey a lot of information. And Victoria, we're fortunate as geologists in Victoria that there are many diverse rock types, and also the exposure of rocks covers roughly that 600 million years of time. Exceptional fossils from international significant sites in Victoria provide a vivid picture of Victoria's geological history and the evolution of life on Earth. There are many special fossils that capture our imagination and are unique to the region. So a team of experts put together a list of about 20 significant fossils, which was then whittled down to 8 candidates. And as you can see, like the beautiful, colourful geological map, the candidates came from right across Victoria and across the, span of time represented within Victoria. So the next slide, we whittled it down to 8 candidates, which wasn't an easy job to do, and I'll just quickly run through them. So the oldest was Isograptus victoriae, a colonial animal from about 450 million years ago. Barraguanathia, one of the first pioneering land plants, about 400 million years ago. Bishop's Whitmorei, a small mammal that was kicking around the feet of the dinosaurs in Victoria 130 million years ago. Janjacetus, which is a forerunner of baleen whales, a very unusual specimen from Janjuk. Pelagornis, which was a giant seabird, much bigger than an albatross, with wingspans of about 6 metres, which was unearthed at Beaumaris. Palaeontology, an unusual marsupial part of the megafauna. Of course, a dinosaur, Lialanosaura, which is about 110 million years ago. And the one that was chosen as the winner, Koolasuchus. The winner was chosen through a public campaign. We had a popular vote, and after a period of time, the votes were totalled up, and Koolasuchus cleelandi was the clear winner, selected by the people of Victoria. And then it was ratified by the government in January 2020 and announced by the Minister of Innovation, Victoria, Danny Pearson. So it's now formally ratified as the People's Choice and appears on the government and the governor's site of state emblems. So tonight, we're lucky, we've got two experts, Dr. Tom Rich and Dr. Anne Warren, and they will tell us why this extraordinary fossil captured the imaginations of the people of Victoria and why it is a worthy state fossil emblem. And it's now my great pleasure to introduce the first speaker, and we'll take questions at the end of both speakers. I'll just say, Dr. Tom Rich is Senior Curator of Vertebrate Palaeontology here at Museums Victoria, working in partnership with his wife, Professor Patricia Vickers-Rich, who's in the audience tonight, from Monash University, and by harnessing the energy of just over 700 volunteers, and I think there's probably one or two of them in the audience tonight as well. Tom's primary research has focused on finding and analysing the mammals, dinosaurs, pterosaurs, birds, turtles, plesiosaurs, and temnospondyls, amphibians like Koolasuchus, that lived in what was polar Victoria between 105 and 130 million years ago. Now, I should point out, when Tom joined the museum in 1974, virtually none of these creatures were known from Victoria, so the entire record is down to the tenacious work of Tom and Patricia Vickers-Rich. So tonight, Tom's going to tell us a little bit about the discovery of Koolasuchus. Thank you, Tom.
Thank you, Dermot. Hello, everyone. It's nice to see you here tonight. I'm here to tell you about Victoria's state fossil, Koolasuchus cleelandi. How did it get its name and the setting the animal lived in? And we'll start by the name of the animal. Koolasuchus was named what it was because of a couple of coincidences. One is that Koolasuchus was living very close to the South Pole of the time. Australia wasn't where it is now. It was far to the south, attached to Antarctica. But there was another coincidence that just was unavoidable. The lady who extracted what we call the holotype, the specimen on which the name is based, was named Mrs. Leslie Kool. And so I couldn't resist the temptation to put her name at the beginning of it, Koolasuchus. Koolasuchus literally means the cold crocodile, because the Greeks had the name Suchus, borrowed from the Egyptians for crocodiles. And when this group of amphibians was set up in the 19th century, there was nothing in the classical literature that named a temnospondyl amphibian. So the nearest thing they could come to was the crocodilian. So it's a crocodilian-like amphibian, not a reptile at all like a crocodile. In 1978, there was very few fossils known from the Cretaceous of Victoria. There was a turtle, Carapucus, one specimen. There were a few feathers from near Coonawarra. And finally, there was a toe bone, 52 millimeters long, the first dinosaur bone found in Australia, and that was it. Now, after 40 years and the help of about 700 volunteers, we have a much more complicated picture of what was in Victoria in the Cretaceous period. And many of these icons represent more than one taxon. Many of them represent half a dozen. And so what's happened in the last 40 years is owing to the efforts of about 700 people who have dug at 3 sites along the Victorian coast. All these sites were located on the shore platform because that's where the rocks are well exposed and fresh. And they produced the picture we now have of these animals. What how did these sites come to be found? Well, they weren't just out there labeled to start with. They were found by systematic prospecting. And two areas were examined in detail, the Otways and the Basque Coast. It turned out in very recent past, we've established that basically the Otway localities are about 106 million years old, plus or minus a bit, and the ones in the Basque Coast are about 130 million. So there's a change in the assemblage of animals that's owing in part to the passage of nearly 25 million years. How did these get found? Because they weren't there to begin with. So what happened was that very hardworking prospectors searched the coast and came up with all these sites here, which you see. All these sites have yielded a few bones at least, and there's actually more of them than are on these two maps. One of the most diligent of these, hardworking of these, was the person for whom the species name of Koolasuchus was given, and that's Mike Cleeland. Mike found the specimens that became what we call the holotype. These left and right jaws were found at a locality on the shore platform near Rowell's Beach, which is in the Basque Coast. And he had found other things that were surprising as well. Now, why was this one surprising? Koolasuchus was surprising for a simple reason. When this group of animals was first discovered here, the youngest ones that were known of this group of animals, we call temnospondyl amphibians, were 45 million years older than what we have here. Since then, fossils have been found intermediate in age in Asia, but still the Koolasuchus is still the youngest member of this group. But there were other surprises in this assemblage of animals that we got in Victoria. Many of them could be quite easily predicted, but some of them were real surprises, and Mike found another one of them. This is a restoration of Koolasuchus by the artist Peter Trussler, and it shows basically a crocodilian-like animal, but it's actually more closely related to a frog or a newt than it is to a crocodile. Another surprise that Mike found was this single bone, the ulna, lower arm bone of a ceratopsian. Now, Museum Victoria has just launched a whole skeleton of Triceratops. But Triceratops is very well known in Western North America. There are literally dozens, hundreds of bones of this animal, numerous skulls. In the southern hemisphere, the ceratopsians, this group of dinosaurs, is known from just 3 specimens. And one of them is this ulna from near Kilcunda, near a site called the Arch. And Mike extracted it from there. So we have on this continent records of the ceratopsians, which is quite unexpected because they're basically a northern hemisphere group as far as we know. The only exception besides this specimen is a jaw that hasn't been seen in 90 years from Argentina, which is a bit younger than this one. But we found in examining the ulna that it's very unique among tetrapods, among land-living terrestrial animals, in the shape of the bone. So there was, despite the skepticism that was originally received for this thing being a ceratopsian, a careful study of it has basically established it as well as you can on the basis of a single bone that, yes, we had ceratopsians in the southern hemisphere here in Victoria. The horned turtles are very well known in Lord Howe Island in very young deposits, but the oldest ones now come from Victoria. There are somewhat younger ones in Argentina, but we now have another surprise, which is getting traces of the oldest horned turtles on the Earth. Now, in thinking about the evolution of mammals, it's been long accepted that the mammals, the placental mammals, the marsupials, and even some other groups of mammals originated in the northern hemisphere and dispersed to the periphery, Australia, Africa, South America. And this has been given the name the Sherwin-Williams effect, after this very famous advertisement for a brand of paint common in North America. What is interesting about the mammals that we're getting here in Victoria is that some of them are older than we expect. And the animal that's identified there is Corybatar, is a rodent-like animal called a multituberculate. It's not a rodent at all. And it's a member of a group of multituberculates that in Northern America thrived from about 100 million years ago to about 60 million years ago, about 40 million years ago. What's interesting about Corybatar is almost 130 million years old. So what's going on? We have at least a 15 million year gap, if not more, between this animal and the oldest specimens that occur in North America. So which way did they go? Did they violate the Sherwin-Williams effect and originate down here and emigrate to the north? Well, on the basis of just a few specimens, you get a little bit, shall we say, leery about making a hypothesis like that, but it's something to at least think about. Likewise, Bishops is a member of a group which is also very contentious. Bishops was originally described as being a possible placental mammal, and if it is older than placental mammals in the northern hemisphere. However, colleagues almost immediately came up with an alternative hypothesis, and that places this animal in a group of southern hemisphere animals that look like placentals but aren't, and radiated in the time of the dinosaurs and then became extinct. Which hypothesis is right? Well, we're still waiting for the definitive evidence because almost all the material we have of this animal is lower jaws. And we don't have good specimens of the rest of the animal, and so the argument is just unsettled. But that's one of the exciting things about what we do, is that a lot of times your ideas have to change and evolve as more evidence comes in. What's the significance of Koolasuchus being near the South Pole at the time? Well, we have good evidence that to the north of us was a place called the Eromanga Sea. This was in northern New South Wales, South Australia, Queensland, and even into the Territory. This shallow sea has evidence of it being very frigid at times. There's a phenomenon when a glacier calves and floats out to sea. Usually the glacier has ground over the underlying rock before it's launched into the ocean. And as the glacier melts, the heavier rocks fall out, the bigger rocks fall out, and often fall into very soft sediment in the bottom of the ocean. These are called drop stones, which isn't a very surprising name at all. But we get them in the Eromanga Sea at about 130 million years. So it was darn cold at times 130 million years ago. Another piece of evidence that we have in those same deposits is a mineral called glendonite, which is formed after another form of calcite that is formed in very cold water in the Ikka fjord of Greenland. Now this form, when it gets warmer than about 0 C, will change into glendonite, these little spiny looking crystals, and these are found along with the drop stones. So that you have these two pieces of evidence that it was cold, really cold, to the north of us, towards the equator, at the time of the Koolasuchus. Now, there's actually evidence now of where those glaciers, some of those glaciers were. We have in northern Flinders Ranges, we've got what are called tillites, which are basically ground up rock that are formed by glaciers passing over them. So we've got a lot of evidence that to the north of us, it was cold at times when the Koolasuchus was alive. Here in Victoria, we have evidence as well. Now, what this diagram indicates is that in the panel above, you have a situation where you have frozen sand, which is saturated with water, and as long as it's frozen, it can support a heavier load of clay over it. What happens is in the summer, when it gets warmer, the heavier clay sinks in this slurry of sand. as far as down as it melts, and then it stops at a very distinct layer, which is the top of a continuously frozen rock. And we have this phenomenon at places in the Basque Coast. So it was cold here at times as well as in other times we have represented. Remember, we're talking in Victoria about 25 million years of our fossil record when the dinosaurs were around, but Koolasuchus is restricted to the 130 million year old interval. Now, what was the environment like? Well, you can have permafrost and you can have fairly abundant flora, diverse flora that has been likened to around a Tasmanian mountain lake, would be one close analogy. So there is the sort of situation we seem to have in the fossil evidence we have here in Victoria at the time, even when it was absolutely frigid. Koolasuchus occurs in the Basque Coast only, and also it occurs basically in the western part of the exposures. And it's interesting that the rocks that they occur in are very coarse by the standards of the rest of the Basque Coast. And this suggests that these animals were living in very high energy environments, very high streams. And to the east, where you get the more of the dinosaurs and you get the mammals, the sediments are finer grained, and they seem to be little channels of that carry bits of clay and stuff like this, but quite different from the gritty sands which yield most of the Koolasuchus. Now, what does this mean in terms of what Koolasuchus was doing in this environment? Well, a good analogy we have with this are the living giant salamanders of China and Japan, which favor a similar environment to that. Now, salamanders are not temnospondyls. They're not, but they're sort of good analogs. And so we think that probably Koolasuchus was like this giant salamander living in a stream sort of like this illustrated below. This seems to be the environment in which the animal thrived. Now finally, there's a very interesting difference between where we get the Koolasuchus and where we don't get the Koolasuchus. You get the Koolasuchus in the older sediments around the Basque Coast. Where they don't occur is in the Otways. Now, what also occurs in the Otways are crocodilians. Now, crocodilians are there, and Koolasuchus is not, and crocodilians are not in the Basque Coast. One explanation that's been proposed for this is that it became warmer between the time of the Basque Coast sediments at 130 million and the time of the Otway coast in 106 million. So that what happened was that the crocodilians, it didn't really favor the colder environment, didn't move in until it became warmer. And the Koolasuchus may have been like many amphibians that were quite happy in colder water. And so this differentiation may have been the key factor in why Koolasuchus survived in Victoria after it became extinct elsewhere. They could survive in a cold environment. And Victoria at the time was one of the coldest environments on Earth. And so that's why we have them here to be our state emblem. Thank you very much.
Thank you, Tom. So it's now my pleasure to introduce our second speaker, Anne Warren. Anne is an emeritus scholar from La Trobe University. Her research centred on Australian temnospondyls, fossil amphibia. With research colleagues, she described the oldest tetrapod from Gondwana and also the world's most diverse early Triassic temnospondyl fauna and the most post-Triassic temnospondyl from Queensland and the last temnospondyl Koolasuchus from Victoria's Cretaceous. So who better to tell us about Koolasuchus than Anne? Thank you, Anne.
Thank you, Bill. Well, Tom Rich has set the scene for the Victoria's fossil emblem, and my job is to show you that it's a worthy fossil emblem. The reason I got involved in this, of course, as Dermot has indicated, is that really I've been the only temnospondyl worker in Australia for about 45 years. There are some younger ones now, but... So, Koolasuchus cleelandi, as Tom said, is not a crocodile, and you can tell that because it has 4 toes on the front foot and 5 on the back foot. And crocodiles have 5 on the front and 5 on the back. It's the only Cretaceous temnospondyl in the world. That's pretty significant. It's the only temnospondyl found in Victoria. It's the only temnospondyl to live with dinosaurs and mammals. In the Northern Hemisphere, a few of them coexisted with dinosaurs, but certainly not mammals. It's much too late. And it's a member of the Chigutisauridae. You don't have to remember that, but you probably will by the time I'm finished speaking. The Chigutisauridae is the longest living temnospondyl family, right? This little group of temnospondyls lived for 140 million years. So I'm going to talk about the origin of tetrapods, the origin of amphibia, briefly, the position of temnospondyls within amphibia, and mostly I'll talk about Australian temnospondyls because I'm the only worker. So, vertebrates have a backbone. Your vertebrates, and the vertebrates consist of fish and tetrapods. A particular group of fish, the Sarcopterygians, and this is one of them, and Eusthenopteron is the most famous Sarcopterygian. These developed bones inside their front limb, in here, and those ended up being the bones inside the limb of tetrapods. So tetrapods have 4 limbs with digits, fingers and toes. A paleontologist from Harvard did an amazing thing. He said most of his life he liked to find paleontological puzzles and solve them. And he wanted to find the missing link between these particular fish, the sarcops, and the early tetrapods. He predicted where it would be found, and he went out there and found it. And that's Tiktaalik. It's probably never been done before that someone has predicted where you'll find a missing link and then found it. So this diagram, series of diagrams down here, show the progression of the tetrapod limb from Eusthenopteron through an Australian Sarcopterygian fish, through Tiktaalik to a tetrapod. And you can see that this blue bone, the humerus, the upper arm bone, is present in all of them. And then we have the radius and ulna, the forelimb bones. And then the wrist area gets gradually more tetrapod-like as we go through. And finally, here in Acanthostega, we have fingers and toes. So Acanthostega is one of the very earliest tetrapods. Here it is again. So tetrapods have digits, fingers and toes. At least I was taught when I was at university that tetrapods have 5 fingers on the front foot and 5 on the back foot, and that is the iconic number of digits. Acanthostega was discovered in East Greenland in the 1930s by the Scandinavians who went out there, collecting. And they found Ichthyostega and an associated fossil, Acanthostega and an associated fossil called Ichthyostega. And they took them back home and prepared them and began to describe them meticulously. And it took a very long time. So when Jenny Clack arrived in Cambridge in the 80s, she discovered that, in fact, a geologist over in the geology department had found a few bones of early tetrapods at the same site. And so she decided to go and collect material for herself. And she had 2 or 3 expeditions there, and they found not only similar tetrapods, but they found better ones. They found better skulls of Acanthostega, several of them, and they found 1, or I think actually 2, whole skeletons of Acanthostega. And they were enabled to show in a lot more detail what was happening with the evolution of tetrapods. So, for instance, Acanthostega was shown to have not the iconic 5 number of digits, it had 8 digits on the front and 8 on the back. That was absolutely astounding at the time. The only other tetrapods these are from the Devonian, the only other tetrapods known with digits had 7 on the, there's one from Russia and the one that lived with Acanthostega. Jenny Clack also showed that the joint between the upper limb and the lower limb, forelimb, was not able to be moved in Acanthostega. So it actually held its limbs out to the side, beside itself, and swam like a fish. If you come onto land, you need to be able to rotate the front part of the limb against the upper part of the limb, and Acanthostega didn't have the correct joints to make that happen. Well, it had the joint, but it wasn't articulating in the right way. So that and several other characters showed Jenny and her colleagues that Acanthostega, much to everyone's surprise, was fully aquatic. It had not climbed itself out onto land, as had been supposed by all the paleontologists prior to Clack. So it was fully aquatic. Why it should evolve digits in a fully aquatic environment, we don't really know, but it did. Living tetrapods, right, are vertebrates with 4 feet with digits, and they're divided into the amphibia and the amniota, quite separate groups. One of the more obvious differences is that the amphibia lay an egg with a jelly-like coat, usually in the water, and that can't survive. The embryo can't survive in that egg for long enough to develop into an adult, so there's an intermediate stage, which in the case of frogs is a tadpole. The other group, the amniotes, have a hard shell on the outside. Inside that is another membrane, and those two together allow the passage of oxygen and carbon dioxide through the shell. They also have a sac inside the egg that provides yolk, right, for nutrition, and they have another sac that holds excretory products. So the little embryo can develop inside that egg into a miniature adult. That allows the amniotes to become terrestrial, and it's a really fundamental difference between those and the amphibia. The other difference I mentioned at the beginning was that the amphibia have 4 toes on the front foot and 5 on the back, and the amniotes don't. They have 5 on the front and 5 on the back. So the temnospondyls, that's what Koolasuchus is, fits in here, right? They're basal amphibians, and one group of small temnospondyls evolved into the living groups of amphibia. So where does Acanthostega fit into this? Well, it's a stem tetrapod. That is, Acanthostega cannot be put into either amphibia or amniota. And that was pretty surprising to people in the early days. It really came from Jenny Clack's work. Surprisingly, because all of these stem tetrapods, this one and the one found with it and the one from Russia and the one from Latvia, and I think that's all there are, 4 of them, they're all from the northern hemisphere. But we have one in Australia. This is Ocynotus, and it's Australia's only stem tetrapod. In fact, it's the only stem tetrapod in the southern hemisphere, in continents that are now the southern hemisphere. It was found at this site in Queensland, in about that position, in a very narrow tetrapod-bearing layer. We have quite a lot of it. Here's a skull, a half skull that Alice found, bits of the lower jaw, very good pectoral girdle, and very good pelvic girdle. But this drawing is a hypothesis, so we don't have the bones linking all of these bits together. It's a reasonable hypothesis. We can show that Ocynotus is becoming terrestrial, but also it's a stem tetrapod. So back to Koolasuchus. It's a member of the amphibia, the Temnospondyli, and then there's a rather difficult family, the Chigutisauridae. So the Chigutisauridae are first known from Australia, from this site in Queensland. If you've been to the Carnarvon National Park, well, you won't recognise it, but I'm telling you, this is the wall of the Carnarvon National Park in the background. This site is found on Rewan Station, which is the turn-off to the Carnarvon National Park. And it's a fantastic fossil site because it's basically a rounded basin which is weathering down pretty slowly from the sides, and it's weathering through the sediments. It's weathering fast enough that it doesn't get covered by grass. There's only one outlet to this basin, so you can see the white layer there is one of these white stripes from the side, and the red layer is one of the red stripes. So it's concentrating fossils, and this is now known to be the richest fossil site in the world for the early Triassic. That is, the richest temnospondyl site. It has more different temnospondyls than anywhere else. And one of them is this one. So this is the earliest member of the Chigutisauridae. It's a skull which is facing upwards, right, in the page. It's covered in characteristic ornamentation, as are all temnospondyls. It's slightly broken across the middle so that this is part of one eye and this is the back of that eye. This should be pushed together. This is the eye socket from the other side. And alongside it is one of the things that's important to Koolasuchus. We have here a complete lower jaw of a Chigutisaur. So I should put this in context. This is a geological timescale. This is the beginning of the Earth, and we're up here somewhere for the moment. So fish evolved down here. We're not worrying about numbers, they change a bit anyhow. Then quite a bit after that we get stem tetrapods, right, Acanthostega, and the one from Australia is a little bit later than that. And then amphibia split from amniotes. And then we've got nothing in Australia, nothing in the way of temnospondyls anyhow, until right up here, which is the early Triassic, almost the earliest Triassic. And here we have the Chigutisaur skull that I just showed you. But at the end of the Triassic, we get a worldwide extinction of temnospondyls. They just go everywhere. And for a long time, they would redate the rocks if they saw a bit of temnospondyl. However, we found one in Queensland, the world's first undisputed Jurassic temnospondyl, not too far from Roma, and it was found by a farmer, of course, in what's known as the Westgrove Ironstone. And this arrow points to where he found it. So the Westgrove Ironstone is running along these ridges. It's forming the ridge. on all of these hills. So it's harder than the surrounds. And the fossil was quite a large one. It was about 3 meters long, and it was encased in harder rock. It was what's known as a concretion, right? So it's harder than the surrounding rock. And what the farmer picked up was a lump about this size of Westgrove Ironstone, but he could see it had teeth. So he sent it down to the Queensland Museum, and they sent a party up, and they collected another couple of bits, and then I came up, and we began to excavate this hillside. This is the hill underneath that arrow. So the concretion had been breaking up and falling down the face of the hill. So we had to clear this grass and then dig deeply down under the soil to look for all the blocks of the concretion. Of course, we got also blocks of ironstone that had no concretion, so it was a pretty tedious exercise. Here's my daughter who's in the Zoom audience, just to embarrass her. Here is Alice scrubbing some of the blocks that have been dug up, right? Because they're covered in soil, you can't tell what's in them until you've scrubbed them. And she scrubbed them, and if you saw bone, then we took them down to a huge map we made down at the bottom of the hill and tried to fit them in. We ended up with the best, almost the most complete temnospondyl, certainly in the Mesozoic. So this is Siderops keeli, iron face, called after the farmer who found the first bit. So this is a reconstruction of Siderops, and it's facing in the same way that this one is. So the skull is pointing down. You can see it's covered in that characteristic ornamentation. Here is one of the eye sockets, and here's the other one. So it's got an almost complete vertebral column because we could fit all the bits together. And the vertebral column goes almost to the end of the tail. This is the shoulder girdle. It's quite characteristic of Chigutisaurs. This is the upper arm bone, the humerus, and here is the hip girdle. And you can see, when you look at the skull, the breaks between the bits of the concretion. So they fit together very nicely. We did miss a few bits, but we didn't do badly. So this became fairly famous at the time, and the public were interested. And at that time, one of the chocolate companies was selling things called yowies. And these were tiny little puzzles that were inside those eggs that they now sell at supermarkets called Kinder Surprises. Siderops made a yowie. They're apparently now collector's items. So at the time that I published this with Mark Hutchinson in the 80s, as you've just heard, Tom and Pat and their 700 assistants were scouring the rock platforms in Victoria, but they were looking for dinosaurs, birds, mammals. But occasionally they found little bits of bone with strange ornamentation. And I guess people suggested temnospondyl, but it was too young. Until Tim Flannery found this bone. Now this was known as the Gok for quite a long time, and that's short for God only knows. It's covered in temnospondyl-like ornament, but it's too young for a temnospondyl. It's 60 million years after Siderops, and nothing had been found in between. It was thought that it must be a dinosaur, perhaps an ankylosaur, and Tom was just telling me that, in fact, in one of the overseas museums, he's seen a cast of this labelled as an ankylosaur. But I had an honours student who was working on temnospondyl jaws, all of the temnospondyl jaws he could find, and he said, look, I see no reason it shouldn't be a temnospondyl. But then Leslie Kool, found the intercentrum. Now this is a part of the backbone. The ribs would fit on here, on the sides, and this is only found in temnospondyls. It's absolutely characteristic of temnospondyls. They have more typical bits of the backbone as well, sometimes, but nothing else has this. And then, of course, Mike Cleland found the two huge lower jaws. And he recognised that these were temnospondyl because of the structure of their teeth, and also, obviously, the teeth went with this characteristic ornamentation. And because the back end of this new specimen was known also from that early Triassic Chigutisaur from Queensland, we recognised this as a Chigutisaur. So here we have the site where the lower jaws were found. Of course, by now it was recognised that several of the other bones that had ornamentation on them were indeed Chigutisaur. They had bones of the pectoral girdle and various other bones anyhow. But no skull material was found until relatively recently. So they now have parts of two skulls. They're characteristically covered in the same sort of ornamentation. This is the back of an eye socket, an orbit, which I think will probably continue around here. And these are still being prepared at the museum. You'll hear more about those, I'm sure, later. So if this is the site, this is the site of other bits of temnospondyl. I think particularly the parts of the pectoral girdle that they found. And you can see that it's a fairly inhospitable environment for, that's a mistake, for getting the material out. Now, I'm pretty sure that at this site, Tom Rich decided to call in the State Emergency Service. I know they came because I was at the top of the cliff. And they came wearing their yellow uniforms and with a yellow, what I call a skidoo, but a yellow thing you pull patients out with anyhow. And they loaded that up with rocks containing Koolasuchus and dragged it up the cliff. And I've thrown my slides away. So there was also a bit of fuss about this in the local papers. Here is the Phillip Island and San Remo Advertiser, which declare that the largest fossil fragment in the world has been found. They'd never heard of big dinosaurs. This is a picture from the 80s, I guess. This is me, Leslie Kool, and others examining one of these fossils. And over here, in the same newspaper, here are various members of that party carrying out blocks of Koolasuchus on a stretcher. So here we are again, it's the same timescale, 60 million years after. Siderops is Koolasuchus from Victoria. So, it's certainly a worthy fossil emblem. It's the last temnospondyl. It's Victoria's only temnospondyl. It survived in Victoria 60 million years after Siderops from Queensland. Did Dermot mention that Siderops has been nominated for their fossil emblem? But we beat him to it. But you can vote. They haven't stopped us voting. I've voted. So Chigutisauridae is the longest-lived temnospondyl family. It started with a very small skull, about this size, in the Queensland early Triassic, and then we have Siderops from the Jurassic of Queensland. That's the one that's been nominated. And here we have Koolasuchus. Koolasuchus was, despite this picture, where it looks fairly placid, it was undoubtedly an aggressive aquatic predator And in this picture, you can see that it's lying in wait for its dinner. And it probably ate some of the large fish that were around there, and I suspect it was carnivorous in that it ate, sorry, it's the wrong word, baby Koolasuchus as well, and it obviously ate young unwary dinosaurs that came down for a drink. So Koolasuchus is indeed a worthy fossil emblem for Victoria, and thank you all for voting for it. That's it.